of the guest speaker. Please,
Okay.
who is taking the
While
citations? Yes, please go ahead.
okay, okay. Good evening, everyone. So while my coordinator is drinking water, let's also try to keep water by our side in case we have to talk. So I will be calling on Mr. Udeme to take the citation of the speaker. Please confirm you can hear me, Udeme.
Yes, hope you can hear me too.
All right, you can go on.
Okay, thank you everyone once again for our time that we have allocated and decided to come and listen to and to learn from this gathering. Um, Not to waste much of our time, I'll read out the citation of the speaker. Mr. Hakeem Mukhtar is an experienced HSC professional currently serving as an HSC coordinator with a strong background in managing safety across high-risk energy and infrastructure operations. He has led the implementation of HSE management systems, conducted hazard identification and risk assessment, and driven incident prevention strategy across multiple sites. His expertise include process safety, emergency preparedness, regulatory compliance, and safety performance improvement. He is a certified HSEQ professional and a recipient of multiple safety awards recognized for his contribution to advancing health, safety, and environmental practice. Hakeem is deeply passionate about monitoring young engineers and is known for his practical, engaging approach to safety training, helping professionals move beyond compliance to truly understand and managing risk. So once again, I would like us to open our mind and keeping and writing materials close to us. I would like to have the honor to welcome to the platform an experienced HSC professional and the current HSC coordinator of the International Energy Service Limited, Mr. Hakeem Mukhtar. Thank you very much.
Over to
Well,
you,
thank
our
you so much.
facilitator.
Thank you so much. I really feel honored to be here today. And I will say a very big thank you for the invitation. And I know today the topic you asked me to come discuss about is a topic that I know that a lot of professionals who are on this course are experts on. And I'll try as much as possible to make this topic to make it as brief as possible because I think process safety as a topic is not just a day's topic. It is a topic that requires at least minimum of 4 or 5 days for one to be able to understand and be, how will I put it, and be an expert in in the training and be grounded in the training. So, but I'll try as much as possible to make this training make it more of a practical section. So please, I want us to please um, manage me as I learn because it is a learning platform for both of us, every one of us on the call. So I'm also learning too. So hope I can shoot. Sorry, let me share my slide.
Yes, please.
Okay. Sorry, I'm trying to share my slide. So can you see my slide now?
Yes, we
Is my
can.
slide visible?
Yeah.
Very good. So once again, good evening, everyone. I want us to get something straight. I am not here today to teach you safety rules. I am here to change how you think about risks. In our profession today, we aren't just paid to be right, but we are paid to anticipate what can go wrong as a safety professional. So, and I'll try as much as possible to make this topic a very practical section, as I earlier mentioned. Hope my slide is still visible, please.
Yes.
Now, before we proceed, have you ever witnessed or been involved in a near miss or safety incident before? You can drop your responses in the chat box. I don't know if I could see the chat box here. No, good. Hello, am I audible?
Yes, you are.
Okay,
Please continue.
good. So I said in the chat box, please, I need more responses, please. Have you ever witnessed or been involved in a near miss or safety incident at work before? Oh, that's good. So I've been saying yes, yes, yes. It was reported. I've not seen anybody writing no. So that means a lot of us have been seeing this before. So I was even anticipating I'll see a no as an answer. So if you are to see a no as an answer, that means probably in that place of work, they might have been hiding or underreporting hazard. Because if you to look at it, hazard is not just something we can just we can run away from. It is everywhere, and every one of us are bound to have hazard in one way or the other. So now I want us to picture something. As a young engineer, someone just like you who just signed off on a permit, everything is checked, everything is approved, and 10 minutes later, there is a release. And the reason for this release is not because procedure failed, but because hazard thinking failed. So I want us to say this in the case of scenario whereby an engineer, who is doing a job of its own, and before the commencement of the job, the engineer went on to sign off a permit. They've done the necessary check, which they need to do, which is the pre-inspection check. They've done their last minute risk assessment, and they have been approved. But unfortunately, at the end of everything, it happened that there is still a release because something failed. And that thing which failed is nothing more than we talking about a failure which is because of an hazard that they did not identify. So sometimes when we're carrying out our job doesn't really speak to we trying to make perfection. It's trying for us to try to ensure we look outside the obvious hazard, because most times, most of us, we just look at the peripheral of hazards. And that is why we are talking about process safety today, and we'll differentiate between process safety and what personal safety is all about. Because in most cases, what makes us differentiate us from other safety professionals is the ability for us to be able to identify what could go wrong with the process of the job we want to do, and not just the personal hazard that is related to what could happen on the job. So in a nutshell, incidents don't happen or incidents don't start as a result of failure, but they start as a result of missed hazards. So the objective of today's section, which we want to talk about today, so generally we'll be talking about distinguishing the difference between process safety and personal safety. We'll also talk about how to learn how to identify hazard in the real world system. We would also be training ourselves on how to apply basic hazard techniques like AZOB, bow tie, also adopt the mindset of a safety professional. So, and with the look of things, most times, most of us believe that safety or it's not everybody's business. Some people believe safety is just about the safety themselves. And I want us to know that today we are going to differentiate between the personal and the process safety and master the bow tie mindset and look at why some of these biggest names in the industry still suffered catastrophic failure. Some people believe anything safety is only about safety professionals alone. But truth be told, everybody has to take ownership. So we need to move from the stage where we think we are just complying to safety, but now we are talking about the ownership of safety. So at the end of this section, I want us to be able to think like a risk engineer, and we should be able to identify hidden hazard, apply systemic analysis tools, and prevent catastrophic failures. And I believe, hopefully, all things being equal, that by the end of this training, you will leave here with only one thing, and that should be for you to start thinking in hazard. So hope you are ready for me. Hello, if you are ready for me, type yes in the chat box. If you are ready for me, please type yes in the chat box. Okay, so thank you so much. So let's start with what is process safety. So when we talk about process safety, what is process safety itself? Process safety is not about slip and trip. Most times when we're talking about hazard, most people be thinking safety is all about slip, trip and fall, walk at height, what will I call it? Hazard of trip and fall, fall from objects from height. Those are not just safety when we talk about process safety. Majorly, those are personal safety. So process safety is not about slip and trips. It is about catastrophe, low frequency events that destroys facilities and lives. So unlike personal safety, where we talk majorly about slip, trip, PPE, those ones are not applicable to process safety when we're talking about process safety. Process safety talks more about system failure. Process safety talks about equipment design. Process safety talks about engineering control. Process safety talks more about we focusing on catastrophic and low frequency events, because zero injury doesn't mean safety. No, for instance, most of us will believe so far there's no injury. If you carry out the job, nobody got injured, then we are all safe. No, you might not be safe if your process safety is not in place, because at the end of everything, you might have zero injury and we will still have cases of people still sitting on a very big disaster. So I would like to challenge today the zero injury mindset. Most people believe that so far you have zero injury on your work site is safe. But trust me, your work site is not safe if your system is poorly designed. Your work site is not safe if your engineering controls are not adequate for the process of the job you are doing. Your work site is not safe when necessary emergency systems are not being put in place. It's not until when there is an injury that you think your work site is not safe. Don't wait until there's a catastrophic event before you know that your work site is not safe. Now, let me ask you a question. Can a facility have a 5-year record of zero lost time injuries and still be at extreme risk of catastrophic explosion? Do you get the question? Can a facility have a 5-year record of zero lost time injuries and still be at extreme risk of catastrophic explosion? Let me go to the chat box. Okay, I'm getting yes. No. Mr. Kingsley, why did you say no? Mr. Kingsley, why did you say no? Please, can you unmute? Mr. Kingsley, please, can you unmute? Why did you say no? Can a facility have a 5-year record of lost time injuries and still be at extreme risk of catastrophe? Mr. Kingsley, I'm waiting for you to unmute, please. Okay, I think he doesn't want to talk to us. All is well. So for everyone who said yes, you are perfectly correct. And I must tell you the truth. There is high possibility of a facility having a 5-year record of lost time injury, and they are still having extreme risks of catastrophic explosion. Because the reason is because personal safety focuses on day-to-day sleep and trip, but process safety focuses on catastrophic, low-frequency events like toxic release or fires that PPE alone cannot stop. Now, for instance, let me give an example for those that are in the solar sector, solar industry. In recent time, a lot of people have been having fire incidents in the solar industry, but most people, they believe, fine, we've successfully installed the batteries, most especially, let me use lithium battery, for example. You've successfully installed the battery, and after installing the battery, you successfully commissioned the battery. But you failed to put BMS program in place, BESS program in place, whereby you can use it to monitor if there is a voltage increase. You can use it to monitor if there is a thermal runway. But at the end of everything, when fire starts, you'll be wondering, okay, how did it happen? But it's because there had been an error in your design. That is the reason why that happened, which you've not put in place systems that can help you, or alarms that can help you to monitor when there is high temperature, or when there is thermal runway. So all these things are things that we are talking when it comes to process. So the difference between process and personal safety is talking about you personally, but process safety is talking about the process. A very good example, someone who is cooking jollof rice. Now, if you are cooking jollof rice, now what you are thinking when you are thinking about personal safety is you are thinking of how you personally will get hot. Can you have burn when you are cooking? Can you have cuts when you are slicing? Those are personal safety. But when we're talking about process safety, we are looking inward. What could happen to the gas cooker? And the gas cylinder, is it corrosive? What are the system in place, or emergency buttons in place, or emergency control in place in case there is gas leakage? Those are when we are talking about process and not just personal safety now. Personal safety is when you be thinking about when I'm using the knife, cut, when I'm hazard of ejection, cut hazard, gun, and all those things. That's when you're talking about personal. But now in terms of process, you are looking inward into the process of how that thing is being done for you to be able to identify what could go wrong. And if you could work more on process safety, the chances of an hazard or the chances of an accident occurring is always very, very slim. So now this leads us to defining hazard and risks. This takes us to defining what? Hazard and risks. Am I still audible, please?
Yes,
Hello?
you are.
Yeah, thank you
Yes,
so
you
much.
are.
Yes.
So when we talk about hazard
Yes,
and
you are.
risks, yeah, thank you so much. So when we talk about hazard and risks, I'm sorry, Madam Engineer Oluwatoyin, please, I want you to help me watch out for the chat box. So in case there is anything that needs to call my attention for, because I'm in the slide mode and I can't be opening the chat box. So thank you so much, ma.
All right.
So when we
I
talk
will do
about
let you know.
hazard, thank you so much, ma. So when we talk about hazard and risks, hazard in this case, we are talking about anything that has the potential to cause harm. Now, in most cases, most understanding of people when it comes to hazard and risks, we are talking about things that can cause injury, things that can cause death. That is what we are thinking of when we talk about the basic hazard and risks. But in process safety, we are talking about what could lead to leakage, what could lead to explosion, what could lead to catastrophic events. That is what we are talking about in terms of hazard when it comes to process safety. I think you understand how I'm trying to explain it now. When we're talking about hazard for personal safety, that's what we're talking about anything that has the potential to cause harm, injury, death, or loss of property. But now, when we are talking about process safety, the hazard in relation to process safety is talking about things that can result to loss of equipment, things that can result to loss of facilities like leakages, catastrophic explosion. So to simply put, a hazard is simply anything with the potential to cause harm. That is, anything that can go wrong is a hazard. Pressure is an hazard. Temperature is an hazard. Fuel is an hazard. Even you as a human being, you are an hazard because through human error, in the course of human error, most especially when we have cases of people having poor valve alignment in the course of maintenance, it is also as a result of human error. Yes, you had me right. Human error, because we ourselves, we are an hazard on our own. So now this takes us to risk. So what is risk? We define risk as a likelihood multiplied by consequences. That is the combination of likelihood and consequences. And the bad news is that engineers fail when they ignore low likelihood. Most engineers will believe the likelihood of the event is very low. But most times, the frequencies are always high. The consequences are always high. So let's assume you are believing that, okay, since the likelihood of this thing is happening. Okay, let me give an example. For instance now, are we together? For instance, the chances of a car, the likelihood of a car having an accident or having a brake failure, or let me rephrase. The likelihood of a car having an accident daily on a Nigerian road is very high, right? But the consequences of when a car have an accident is not up to the consequences of when an aeroplane crash. But the likelihood of an aeroplane crashes is very, very low. Do you agree with me? Do you agree with me? The likelihood
Yes.
of an aeroplane crashing is very low, but when it crashes, the consequences is always high than when the consequences of a car having an accident. So because you believe that the likelihood of an aeroplane is very low, crashing is very low, that doesn't mean you should now believe there is no risk. There is risk because the moment the consequences is high, a high consequences and low consequences is very, very high. Using a risk matrix analysis, for instance, let's say a 5x5 matrix. A 5x5 matrix. Let's assume the likelihood is 2 and the severity, which is the consequences, is 5. So 2 times 5, is it not 10? Is it not still very high?
It is.
It is very high. And a likelihood is 5. The consequences is 1. If you were to look at it, 5 times 1 is still something moderate. Do you get what I'm trying to say? So with the look of things, where most engineers fail is because they ignore low likelihood. They believe because the chances of it happening is very low. So because of it, they let it slide. They overlook the hazard. And at the end of everything, the outcome is always a total facility loss, and it is always very dangerous. So in a nutshell, the trap that most engineers fall into is because they believe there is no likelihood. But the reality is that it always have a critical impact. So I want you engineers to know that when engineer fails to ignore events that are unlikely to happen, the frequency or the consequences of the incident happening are always very high. So now we move to hazard identification, hazard tools. At this stage that we are getting to, I will encourage us to start getting our biro and pen ready, our book and pen ready, because I'm trying as much as possible to make this class as practical as possible. So, and I want it to be as interactive as possible. So we're talking about hazard identification tools. We have different hazard identification tools. We use tools like HAZOP, we use tools like AZID, we use tools like what-if analysis, job safety analysis. But I want you to know today that tools don't prevent accidents, but thinking does. Tools don't prevent accidents, but what? Thinking does. So I want to ask every one of us a question. And this question is something I want us to always deal with, because that is the main purpose of the what if analysis. So I'll be skipping ASOP studies now, because I still have a very detailed slide on ASOP studies ahead, and a practical illustration what we'll be dealing with in ASOP studies. And job safety analysis is very simple. I believe all of us understand job safety analysis. Majorly what we are trying to do with job safety analysis is for us to break down the tasks into stages, and then we'll now start looking at what could go wrong with each stages when we are talking about the job safety analysis. So for the what if analysis, I want you to always ask these 3 questions every single day when you are working. And the questions are, number 1, what can go wrong? For what if analysis, the questions are, what can go wrong? So what happens next? The second question. And most importantly, what stops it? Do we get the question, and are we jotting down? Question number 1, what can go wrong for what if analysis? Question number 2, what happens next? And question number 3, what stops it? That is, we are trying to talk about trying to identify the what if analysis. What if analysis. So this goes a long way. So, but even though ASOP uses some guide word, which we'll be talking about in the next slide. So ASOP generally, that stands for what? Hazard and operability studies. HAZOP means hazard and operability studies. HAZOP studies stands for the hazard and operability studies. It is a structured, systemic, and team-based techniques used to identify potential hazard and operability problems in a process plant, system, or procedure before they cause an incident. So generally, what HAZOP is trying to stand for is for you to be able to look inward. It is a technique for you to identify potential hazard that will affect the process, the system. And majorly, I overheard the NSC Ikeja chairman speaking about someone taking us on safety in design or safety in design. So HAZOP starts from the planning stage. HAZOP starts from the planning stage. Even before you start the project, you start the installation project, you to carry out your HAZOP. So HAZOP was developed by the Imperial Chemical Industry in the 1960s and has since become the gold standard for process hazard analysis across the energy, chemical, oil and gas, and pharmaceutical industry. So I want us to know something today. And that is the core philosophy behind HAZOP, because it is very important for us to know that the core philosophy behind HAZOP, even though it is simple, but it is very, very, very powerful. Most accidents don't happen because people are careless. Most accidents don't happen because people are what? Are careless. They happen because something in the process deviated. And that is what HAZOP is going to be teaching us, because HAZOP will be speaking more to deviations. We'll be talking about the guide word and the process parameters when we are talking about HAZOP studies. So we are going to get there. I try as much as possible to make it look like a workshop, because Madam Oluwatoyin said she wants it to be as practical as possible. So be ready for calculations, be ready for us to do practical section. There are a lot of exercises for us. So I want us to know that most accidents don't happen because people are careless, but they happen because something in the process deviated from what was intended. You know, for instance, you have a plan that, okay, this is what you want to do. But in the course of doing that thing, or in the course of execution, something deviated. That is the design plan which you designed in the course of the process, in the course of the planning stage, you end up mixing it out. And no one anticipated it. So that is why it is expected of you as a safety professional, which I earlier mentioned, that you should start thinking, I said safety professional, sorry, as an engineer, you should start thinking hazard. That is what can go wrong. What can go wrong? And this is one of the things that I think always causes issue in my family. You know, for instance, if they are doing something and I'll be like, don't you think this will go wrong? Don't you think this will go wrong? They will tell me I have a negative mindset. Oga, there's nothing like negative mindset. As a professional, it is expected of you to always identify or anticipate the things that can go wrong. That is why you should always think beyond the obvious. And I believe this happens to most safety professionals too, whereby when they are doing things, you'll be thinking the next thing you start seeing them doing hazard analysis almost immediately. What can go wrong? What can go wrong? So knowing this, HAZOP forces a team to systematically ask, what if this process doesn't behave exactly as designed? So that is the question we ask ourselves. What if this process doesn't go the way that we plan to design? So because you might be planning that this is how you plan to design it, this is how you plan to execute it. By the end of everything, at the point of execution stage, it end up failing. Now we are getting there. So how do we conduct HAZOP? The question is, when is a HAZOP conducted? HAZOP is typically carried out at these 5 stages. HAZOP is typically carried out at this 5 stages. So number 1, the first stage that HAZOP is being carried out is during the design stage. That is before the plant is being built at all. Before you identify so during this period, when you are still in the planning stage, you try to identify and eliminate the hazard as early as possible. And trust me, the cheapest way of fixing an hazard or eliminating an hazard is during the design stage. This is not only applicable to we that we are in the oil and gas sector, that we are in the process sector, manufacturing sector. It's also applicable to those also in the construction sector. That is why we talk safety in design. That is, in the course of you designing, you should start thinking of how can you eliminate hazards in the course of the execution, in the course of while you are designing your project, while you are designing the building. That is why a lot of people end up losing a lot of funds, because they didn't put safety in design into place. They didn't think, what can they do in case of maintenance? How will they manage this in case of maintenance? At the end of everything, they will start destroying wall, breaking things, which will cost them more because they didn't put all this in place while they are in the designing stage. So the next other stage is before commissioning. So now you've surpassed the designing stage. After the designing stage, you've mobilized to site, you've done the execution of the job. So, but before you now commission that this job you are done, people can now start using it. That is why you will keep hearing in the oil and gas sector, they will say they are testing. After they've installed, they are testing. All what they are trying to do is they are trying to verify what they've built, if it matches the design that they intended to design. So what they are trying to do is, does it meet up with the speed, with the pressure of what they want that machine to provide? So in the course of the before commissioning, so they try to verify. Start major modification. When there's a major modification, maybe probably after they were before commissioning or in the course of them trying to verify, they observe that there are some things they need to modify, and they end up modifying. So any significant change to equipment, process, or operation. So when you do any modification, you are meant to also conduct another HAZOP. During periodic review, which is always advisable to be every 5 years for operating plants, you have to carry out a revalidation exercise. Then you are also meant to carry out HAZOP to know if that operating plant that you've been using for the past 5 years, if it has introduced another new hazard. And after an incident has happened, maybe a major accident has happened, you would also do an HAZOP study for you to be able to understand if there was any failure in the process or if there was any deviation and the reason why there was that deviation. So in a nutshell, I will use the acronym DBAPA. 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 Do you get? So that is the design stage, before commissioning stage, after major modification, periodic review, and after a major incident. So I want us to please note that the earlier a HAZOP is done, the more cost-effective it is. I repeat, The earlier a hazard is done, the more cost effective it is. Because fixing a hazard on paper costs virtually nothing, unlike when you are fixing it after construction, which will end up costing you millions of naira. So now, before we proceed to the next slide, I want us to understand something. Most people believe this hazard is something you do alone. But trust me, you can't do it alone. That is why we have what we call the hazard studies workshop. For those that are in the engineering firm, that are in the oil and gas sector, that are in the construction sector, process sector, manufacturing sector, where they deal with process safety, you would understand very well that before any job is being done, in the course of the design stage, and during the stages that I've earlier mentioned, there is something we call hazard workshop. So this hazardous workshop is always set up of multidisciplinary teams. So we have different teams members that joins this hazard workshop. So which one of them is the hazard chairman, majorly the facilitator? We have the process engineer, we have the instrumentation and control engineer, we have safety representative, operation representative, we have maintenance engineer, and finally, we always have an hazard recorder, like a secretary, that will be taking note of all what is being mentioned. So the good thing about you setting up an hazard team is that with each person, they are in different field of, I mentioned instrumentation, piping, process safety and co. Because they have different lenses. Everybody, it's just like, for instance, let me use this as an example. Writing number 6. If I'm standing at the left-hand side of number 6, I might be seeing 6. And if another person is standing at the other side, the person will be seeing 9. So the good thing about this hazard studies workshop is for people to be able to have different lenses and have diversity of perspective in what makes this hazard effective. That is the diversity in their knowledge, the diversity in what they are seeing is what makes this hazard more effective. So how do we build the building block of hazards? The building blocks of what? Hazards. So many people have been hearing me using some words, design intent, deviation, blah, blah, blah. So I want us to understand that in hazard, you must understand 3 key fundamental concepts. You must understand 3 key fundamental concepts. Number 1, design intent. That is the intention of the design, what you want that design to achieve. The design, why was that thing being designed? What do you want that design to look like? The picture of what the design wants to look like. It's just like someone wants to build a house. That's in an architect did. That an architect will first build a caricature model of the house, that they'll put a model 3D or 4D or 5D, depending on the teeth they are using. Is the design intent, how you want the building to be after it has been fully constructed. So this is what the process is supposed to be. This is what you intend the design to be. Now, for example, pump 101, you want it to transfer liquid from tank A to reactor B at a flow rate. Look at the watchword. You are designing a pump, but this pump now, what you want that pump to be able to flow at the rate of 15 meter cube per hour. You understand what I'm trying to say? That is the rate you want it to at the pressure of 2 bar. Do you get? So that is the rate you want the liquid to be transferred. So the design intent is the baseline. The design intent is the foundation, the foundation of what you want to construct, the foundation of what you want to do. In ISO, we call it scope. That is the scope of what you want it to cover, scope of what you want that thing to do. So in ISO, so design intent is what you want it to aim, what you want that thing to be like. So that is design intent. So when we talk about deviation, just in the layman language, deviation, that is moving away from what you wanted it to be. That is what we call deviation. Moving away from what you plan it to be. For instance, you plan to build a road, blah, blah, blah. And at the end of everything, I'm trying to use this because I don't know if most people are in the oil and gas sector. So that's why I'm trying to bring in construction that can easily be relatable. I'm trying to bring in maybe manufacturing that is that can be relatable. Now, for instance, let's assume you want to build a line from point A to point B. And that point A to point B, you plan that that line that you're trying to build should be in a spherical shape, that is square. And the moment you are building it, the line has started changing to rectangular. Is that the design intent or deviation? Let me see your response in the chat box. Is that design intent or deviation? Now, for instance, you are trying to deviation, good. Now you are trying to build something that is in spherical shape and you are ending up building something rectangular. That is deviation. So deviation means that, thank you so much, thank you so much, thank you. This shows everyone is following me. I'm very, very grateful. So a deviation means that you are making a departure from the design intent. That is what you really intended to build. You're already diverting from it. So that is where ASOP generates deviation systematically by combining guide words. We have guide words like no, more, less, as well as those are guide words. We are getting there. And so when we are talking about guide words, so guide words are telling us what we are no, more, less. Those are guide words, and we are talking about the process parameters. So process parameters, that is when we talk about process parameter like flow, pressure, temperature. So those are process parameters. So for nodes, a node is a specific section of the process. It is a specific section of the process. It can be a pipe, it can be a vessel, it can be a heat changer, it can be a pump that the team examines at one time. So the ASOP team works through the process node by node. That is, you pick it node by node. If it is a pipe, you are trying to do, you pick the pipe, you try to look at the design intent of the pipe. You look at if there's any deviation with the design of the pipe. Do you get? So with that, you'll be able to know what are the process parameters in relation to pipe. Is there a flow in the pipe? Is the pressure sufficient in the pipe? All those things are things you look out for when you're talking about the nodes. You'll be picking them notes by notes. We'll do something like a real life example too. So using piping and instrumental diagram as the primary reference. Hope I'm still making sense, please. I hope I'm still making sense, please.
Yes, you are.
Yeah, thank you so much. So now this takes us to the guide words and parameters I've been talking about since. So when we're talking about the guide words and parameter, this is the art of the ASOP. You must understand this, and it's very, very important. And I'll still tell you how we combine these guide words and parameters together. So when we talk about guide words are simple word that expresses the nature of deviation. You know, we've been talking about deviation, and we understand what deviation is now. That is trying to divert or taking away from the design intent. That is what we call the deviation. Now, guide word is now telling you what are the words in respect to that deviation. They apply to process parameter to generate meaningful deviation for the team to analyze. Now, let's look at the screen. Now, look at no or not. When we're using the guide word no or not, it means complete negation of the design intent. That is, you have deviated completely from the design intent. More, that is quantitative increase. More can also be high. More can be over. So more quantitative increase above design, less reduced. You understand? For instance, now, I gave an example. Let me go back to the previous slide. I gave an example in the previous slide where I was talking that we are trying to have a flow rate pressure of 50 meter cube per hour at 2 bar pressure. Do you get what I'm trying to say? Now, for instance, now let's assume at the end of the design, the pressure is now higher than the 50 meter cube per hour at 2 bar pressure that we plan to do. So we'll be hearing more pressure, right? That is now more. Let's assume it is lower, less pressure. That is, it is now below what we plan to design initially, as well as something additional is present. That is, there is a contamination, as well as part of, reverse, other than. So we have a lot of guide words like that. but these are the standard guide words that we'll be using in the course of this training. So common process parameters, we have different common process parameters, which is flow, pressure, temperature, level, composition, viscosity, reaction, pH, time, speed, voltage, and signal. So now let's discuss how to combine the guide words and parameter. So, but before we discuss that, please, I want every one of us to screenshot this slide. This slide I am currently on, I want every one of us to screenshot it because we'll be using it in the next presentation. So at the count of 3, 3, 2, 1, 0. Yeah, thank you. Now, how do we combine these guide words? So we combine these guide words. For the combination of the guide words and parameter, you take a guide word and we apply it to each other. Now, look at this. I was saying something earlier in terms of, I used an example of the 50 meter cube per hour at 2 bar pressure, which I mentioned earlier. Now, look at this guide word. Now, more plus flow means high flow. So, and you know, I said something about newts earlier. Newts can be pipe, newts can be vessel, and co. So now let's assume the node we're analyzing is a pipeline. I get what I'm trying to say. Then we'll now be saying, okay, more flow in the pipeline. It means what? High flow rate in the pipeline. That is the design intent. The flow is now above the flow we projected in the design intent. No flow. No flow, it means no flow. That is, the pump has failed or the valve has been closed. Less pressure, low temperature in the reactor. The reverse flow, that is, there's a backflow into the upstream vessel, depending, you know, I told you nodes. Now, the node we are using here, now for the reverse flow, the node we are using here is what? Vessel. Hello? Now, I want us to do something so that we'll understand very well. Now, more flow, high flow rates in the pipeline. So what is the guide word? What is the parameter? I'll call someone randomly. What is the node we are using here? What is the node we are using here? Mr. David Alabi, can you unmute, please? Mr.
Vessel.
David Alabi, can you unmute? Yeah, thank you so
Vessel.
much. No. Look at the first example. What's happening? Go back. Can you see the first one? I said more flow, more plus flow. Then the meaning that I was giving you is high flow rates in the pipeline. So what node am I using there, Mr. David Alabi?
Pipeline.
Yeah, good. So, and what is the guide word there?
More.
The guide word is what? Exactly.
More.
What is the, yeah, and the process parameter is flow, right? Yeah, good.
Correct.
Yeah, thank you. I don't know. Let me just randomly pick another person. Mr. or Miss Folarin Shobola. Mr. or Miss Folarin Shobola, are you with us? Are you with us? Mr. or Miss Folarin Shobola? Okay, I think the person is not with us. Okay.
Person has replied yes.
Okay, can the person unmute, please?
I'm with you, sir. Good afternoon.
Good afternoon, sir. So for less temperature, less plus temperature, low temperature in the reactor, what is our node? Low temperature in the reactor, what is our node?
Our node is the reactor. Reactor is that's the connection point.
Yeah, reactor is the node. What is our guide word?
Our guide word is temperature. Less temperature.
Less is our guide word. Why the parameter is temperature?
The temperature, yeah, thank you.
Yeah. Engineer Gabriel Oyeola. Engineer Gabriel Oyeola. Please, can you unmute? Engineer Gabriel Oyeola, can you unmute?
Yes, I'm with you.
Yeah, thank you so much. So,
all right.
Yeah, I can hear you. For reverse flow, which speaks to backflow into the upstream vessel. Backflow into the upstream vessel. What is our deviation?
That's the
What is
hello,
our
come again.
deviation? Reverse plus flow. The meaning is backflow into the upstream vessel. What is our deviation?
Deviation is the backflow.
Yeah, good. Deviation is backflow. Then
Yes.
what is our nodes? The node is the upstream vessel, and the reverse is the guide word, and the parameter is flow.
That is flow, yes.
Are we together?
Reverse.
Do you get that?
Yes.
Do we get that?
Yes, yes. Very clear.
Yeah,
Thank you.
good. Yeah, thank you so much. So let's move on. Let's move on. Thank you so much. So now, okay. So we are still on the same page. And so now the interesting thing about this is, since we understand what deviation is, so for deviation is the meaning for what that more flow is. You know, by the time you interpret more flow, high flow, that is the deviation. The more is the guide word, the flow is the parameter process or the process parameter, while the pipeline is the node, and the deviation is the high flow rate, which we get there. So now I want us to note that each deviation can trigger a structured set of questions. Each deviation can trigger what? A structured set of questions. Now, for instance, we've used the guide word more plus flow, which gave us the meaning high flow rate, which is the deviation. The deviation is the high flow. That is, the flow is now higher than the design intent. You get? So that is when you now start asking questions like, what are the causes of this deviation? You can jot it down. What are the causes of this deviation? What are the causes of this deviation? You can. What are the consequences if it occurs? What are the consequences if it occurs? What are the consequences if it occurs? What safeguards already exist to prevent or detect it? What safeguards already exist to prevent or detect it? Sorry. What safeguards already exist to prevent or detect it? Is the risk acceptable with existing safeguards? Is the risk acceptable with existing safeguards? What additional actions or recommendations are needed? What additional actions or recommendations are needed? Now, you know, after you've used this, your guide words and parameter to be able to identify the deviations for each node that you're trying to look. So the first thing you know is that, you know, the moment you know what your node is, you've identified the deviation, the next thing you think is, what are the causes of this deviation? So you start thinking, what can trigger, what can lead to these causes? Why are we having high flow rates? Do you get? So the next one is, what are the consequences? What will happen when this high flow rate, when it occurs? You would also be asking, what are the control measures? What are the safeguard systems that you've put in place, or the emergency detection systems? Emergency detection systems that you've put in place that will be able to detect it when there is a leakage or something. Do you get? So, and you also be asking yourself this question, is the risk acceptable with the existing safeguard? That is, you are trying to check if that existing safeguard is sufficient for the risks that you've identified. Then if the risk is not acceptable for the existing safeguard, then you start thinking of what additional measures, what additional control measures you can put in place. Now, this is an example of a hazard worksheet. You can screenshot. But note, this is not how it is. It is always in a tabular form. You understand? It is always in a tabular form. So this is how an hazard worksheet will look like. So every findings, after you've done your deviations, you've identified your deviations, you've analyzed the risks, you've been able to identify what causes the deviation, the consequences, the safeguard you've put in place, the risk rating, the recommendations, and the action. So you now put it in your worksheet, which is always in the tabular form. So every findings that you've already gotten will be recorded in a structured worksheet.
which is the backbone of the ASOP study. A typical ASOP worksheet has this column. It has the column for node. I think you all understand how to identify node. It has the column for parameter. When I was talking about flow, pressure, temperature, viscosity, and co. It has the column for guide word, no, more, less, as well as, and so on and so forth. It has the column for deviation. You know, when we say more flow, that is high flow, more pressure, over pressure, high pressure. Do you get? That is the deviation. It has the column for deviation. It has the column for causes. This is when you start analyzing what caused that deviation. The consequences. It has the column for consequences. What are the consequences if these deviations are not being managed? What are the safeguards we've put in place, like the control measures we've put in place? It has the column for it. It has the column for the risk rating. Is it high? Is it low? Is it medium? What is the likelihood? What is the severity? So it has the column for that. It all depends on the risk matrix you're also using to know what you want to use. If you are using the 5x5, 6x6, depending on the risk matrix you want to use. So it also has the action and recommendation. That is the action and recommendation that you want to put in place and the necessary action owner. An ASOP worksheet is always, an ASOP worksheet should always be completed with an action owner. You have to dedicate an action owner to the person that needs to close out it. Now let's look at the examples on the screen. Now the node here is pump P101 to discharge line to reactor R201. That is, the node is for us to what? For the discharge line, which is the P101 to discharge to what? To the reactor R201. So now what is the parameter? That is the flow rate, how we want it to flow. Maybe the rates that we want it to what? To flow. Now, the guide word there is no. So don't forget what I said earlier. No plus flow will now be what? No flow. That is, maybe the reactor has been shut down, it has been closed, the valve has been closed. That is the deviation. So the deviation there is now speaking to what? No flow from pump to reactor. That is, the design intent is that there should be a flow from the pump P101 to reactor 2101. But unfortunately, there is no flow according to the guide word. So there is a deviation, that is no flow from pump to the reactor. So what are the causes? So when I start thinking of what are the causes, what can cause no flow? One of it is maybe there's a trip from the pump P101, the discharge valve has been closed, the junction line has been blocked. So you are thinking already about the root cause. What are the causes that might affect this process of a flow being successfully done from P101 to the reactor 2101? So what are the consequences? That is, what are the aftermath? What is the aftermath? What is the consequences of these causes? One of them is the reactor will be starved of feed. Reaction run will be possible if eating continues. Product quality might be lost. So that is the consequences. So we're thinking of how can we safeguard it? Now, I mentioned something in terms of safeguards. When we are thinking of safeguards, you should always think of two things. Safeguard in a layman word, we can call it the control measures that has been put in place. So number one, when we are analyzing the consequences, we need to also consider the safeguard that has been put in place before and the safeguard that we still need to put in place. Do you get what I'm trying to say? So looking at it, what I mean by safeguard that has been put in place, and okay, let me explain like that so that we won't get it confused. For instance, now, okay, we all know that when we are driving a car, there's an hazard. The hazard can be as a result of overspeeding, right? And overspeeding can be as a result of different factors, which could be maybe because the person is under the influence of alcohol, maybe the person is under pressure to get to somewhere on time and things like that. So there has been a system put in place to prevent overspeeding, and that is the braking system. That is, in case you are overspeeding and you lost control of overspeeding, which is the consequence. Losing control while you are overspeeding is a consequence. So there is a safeguard that has been put in place, which is the braking system. That is for you to be able to apply a brake so that the overspeeding issues will not happen, right? Now, in a case whereby you now apply the brake now fails. I get what I'm trying to say. There is also further control measures being put in place. That is where your airbag comes in place. That is where your seat belt comes in place. Are we getting what I'm trying to say? So, in the terms of safeguarding of a process, machine, or equipment, what we always consider is what are the things that can prevent that causes, and what are the things that can detect it. Do you get? That is, it can prevent and it can detect. Do you understand what I'm trying to say? Depending on the kind of process we are trying to work on. Hope I'm making sense, please. If I'm making sense, please type yes inside the chat box. If I'm making sense, please type yes. Yeah, thank you so much. Thank you so much. So when we're thinking about safeguard speaks majorly about what you've put in place to prevent that thing you've preempted. That is why when you are doing your HAZOP, it is very necessary in the course of design. So in the course of the design, they've preempted that people can be overspeeding and they can lose control in the course of overspeeding. So due to that, they put a braking system in place. And in case braking system fails, what else can still help? That is where they have what we call the airbag and the seat belt. So the risk rating, which we all know, if it is high consequences, we have the recommendation, and we also have what the action owners are. So when we're talking about the risk rating, we will have done our likelihood and severity. Then based on the risk rating we are using, we now determine if it is going to be high consequence or not. And recommendation will now be, what are you recommending? What are the further process action you think they need to put in place? Like install automatic reactor, heat shutdown on low flow signal, review alarm response procedure, you understand? And also action owners. Who are the action owners? To ensure these are being closed out. That is when we think about the process engineer, instrumentation team. We can screenshot this too. So I would like us to stop here before we turn this class into a full HAZOP training workshop. The training is not for HAZOP training alone. So I think we've been taking longer time on HAZOP. But I believe we understand the basics of what HAZOP is. So, and I want us to know that these worksheets that I drew on the that you are seeing on the screen, please, who are those drawing on the screen? These worksheets that I showed you are always in a tabular format. That is node, parameter, guide word, deviation, consequences, safe guide, risk rating, action and recommendation, and action owner. They are all always in a tabular format, just like we do our risk assessment. You understand? So, and looking at this example I gave us is only one node. And the node we are working on, based on the example I gave us here, is a node of pump P101 discharging line to a reactor R201. Now, let's come to think of it. This is just one deviation that we break down like this. One single deviation, which is no flow from pump to reactor. That is one single deviation that we are talking about here. Now, let's multiply this across the entire plant with hundreds of nodes. You will begin to understand the power of HAZOP. So HAZOP studies is very, very comprehensive. It's very, very detailed. So on this note, I would like us to stop here, as I earlier said, for the HAZOP, and let's move to other things. So if you understand all what I've said so far on the HAZOP, please type yes inside the distance. Type yes. Type yes. Yeah, thank you so much. Thank you so much. Hope I'm not taking us to the classroom. It is a presentation, a webinar, but I'm very sorry. I'm trying to make it like a classroom. Type yes. Yeah, thank you so much. So we move on to the next phase, which is talking about the simple hazard thinking model. So, I mentioned earlier in the beginning of our presentation that we have different types of hazard tools, and one of them is the what-if analysis. So, and the what-if analysis is one of the simple hazard thinking model, and I believe engineers should consistently ask these three questions. And what are the questions? The questions are, what can go wrong? What are the consequences? And what control exists? What can go wrong? What are the consequences? And what control exists? So when we're talking about what can go wrong, that is, what can happen, you understand? So what are the consequences? We are talking about what will happen next. When the thing that we project to happen has happened. So what is going to happen next? That is the consequences. And when we talk about the control, what are the things that can stop it? What are the things that can stop it? Like the example I gave, when someone, when you are driving on a high speed, what can go wrong? I can lose what? Control. What, do you understand what I'm trying to say? That is, they can, so I can lose control. And with the look of things, and what can go wrong? They can, in the course of I losing control, my brake can fail. So what is the consequences of that brake failing? Do you get? What is the consequence of that brake failing? There can be even fatality. That is, the person who is driving can die. So what are the control measures that we put in place? That is when we're talking about the airbag and the seat belt. So note, if you ask these three questions consistently, you will prevent most incidents. I repeat, if you ask these three questions consistently, you would what? You will prevent most incidents. So now let's go to hierarchy of control. So when we're talking about hierarchy of control, and this one, I want us to always know, the hierarchy of control plays a major role in our planning stage. Hierarchy of control plays a major role when we are doing when we are using any of our hazard identification tools. And most especially, the best of it all is to always ensure we use the elimination. That is, we should try as much as possible to see if we can remove the elimination completely. So engineers must apply controls in this order of effectiveness. So the best of it all, when you design a solution, always remember what? The hierarchy of control. So number one, elimination, removing the hazard entirely. Substitution, replacing a hazardous material with a safer one. Engineering control, using relief valves or shutdown systems to what? To redesign the flow or to stop the flow or to put a stop to what failed. Those are the engineering controls. Administrative controls, speaking to the procedures and the training. The PPE, which is always the last line of defense and not the first. But in today's that we are, when we are thinking of, please, Madam Oluwatoyin, please, can you help us mute the person who is on? So while we are thinking of hierarchy of control, the mistake most engineer does today is that in the course of their hazard identification, the next thing they start thinking of is PPE, PPE, PPE. They do not overuse or overbeat the hierarchy of control, the elimination, the substitution, the engineering control, and administrative control. We even have some people that, for instance, when you are using PPE, always ensure the PPE you're also writing is very, very specific. You cannot just tell me PPE, hand glove. We have different types of hand glove. We have cotton hand glove. We have rubber hand glove. So we have hand glove that are cut, they have resistance to puncturing. You understand? For those people that are into carpentry, that the hand glove will not allow penetration of nails. So we have rated hand gloves that can withstand electrical voltage in the electrical sector. So when you are even writing the PPE, don't just write hand glove, don't just write coverall. Is it fire retardant coverall? Is it high visibility vest? You should be very specific. Even the adults we are using, the adults they use in construction is different from the hazard they use in electrical sector. Electrical sector is class E as class E adults. So it depends on the kind of adults you are using. You have to also be specific. So when you design a solution, always remember the hierarchy of control. Elimination is your gold standard. PPE like gloves, masks is always your last line of defense, not your first solution. If you are relying on PPE to save the day, your design has already failed. Your design has what? Already failed. So engineers must design hazard out of the system. And how do you design hazard out of the system? By ensuring you think of how can I eliminate it first? After you've ensured you've done everything possible to eliminate it, and you've exploit that, then the next thing you move towards substitution, then you move to engineering, administration, and so on and so what, and so forth. Now let's go to this. A scenario. A contractor needs to perform welding earthwork within 15 meters of a live gas pipeline. A contractor needs to perform welding earthwork within 15 meters of a live gas pipeline. Now, there's the task or the classwork all of us want to do now, based on the knowledge of the hierarchy of control I just finished talking about. So let's rank these controls from the most effective to the least effective. Number one, providing the weather with a fire retardant suit. Number two, using a continuous gas detector. Number three, shutting down and purging the line. And number four, signing a earthwork permit. Now let's line it up according to the rank from the most effective to the least effective. I'll be in the chat box watching out to see the correct order. So which is the most effective to the least effective? Yeah, great. I can see someone already getting it. I need more responses, please. I need more responses, please. I've even given you answers in front by putting the process in front of it. Yeah, good. So, yeah, good. Anybody that doesn't get it right, you are not here, you are wrong. So, the most effective is 3, and that is shutting down the purging line. And followed by 2, using continuous gas detector. Followed by 4, signing an earthwork permit, and followed by the last, which is the providing the weather with fire retardant suit. So always remember that PPE is the last resort. So we should always ensure that we follow elimination. That is why I even wrote it, to make it easier, I even wrote the hierarchy in front of it. Now let's start the exercise for the day. So we are getting there gradually. So case study number 1. So now this is a case study. Let's use a Nigerian context, a pipeline incident. In Nigeria, we see this recurring pattern, often where small hazard escalates because they are silent risks. You know, in the case whereby we have a scenario, and this is the scenario. A pipeline developed a small leak due to corrosion that was initially ignored. Look at the sequence of events. A pipeline developed a small leak due to corrosion that was initially ignored because it seemed minor. That if you are looking at it, it is minor now. It is nothing serious. Then the leak eventually resulted into a vapor cloud that found an ignition source and leading to a massive explosion. Now, looking at this case study, there's a sequence to this event. And the sequence of the event is as a result of a small leak, which was initially ignored. That is, the person identified a small leak. And when this person identified the small leak, the person still what? Ignored it. So that shows that there is a failed inspection program. Because the moment you carry out an inspection, you identify something and you still didn't do the needful to ensure that that is being closed out immediately, which is the major issue most of we safety professionals and engineers are having. We only do inspection just for record keeping. We only do inspection to keep that we've done our task, we've done our deliverable, but we fail to follow up to ensure the needed control measures, closeouts are being done, which makes us fail. So with the look of things, this person saw the small leak in the course of the inspection and he ignored it. Then this resulted to a vapor cloud because gradually, you know, it's just like an adage that says a drop of water will make a mighty ocean now, if I'm right? So with the look of things, this vapor will start building up. And at the end of everything, it soars explosion, which is the main process of process safety. Are we there? So now looking at this, in the course of Hope I'm still audible. Hope I'm still speaking because I can see it's saying my internet is not stable. Am I still audible, please?
Yes, you are.
Yeah, thank you so much. So delayed emergency response also resulted to this because in the course of the vapor cloud building up, there should have been a safeguard in place that will have identified that there is already a buildup of vapor cloud, a leak or something, whereby it will have caused an alarm even before the ignition. So that means a delayed emergency response is also there and catastrophic explosion due to weak engineering controls that were not put in place. So majorly, to be candid with you, this happens a lot in Nigeria. We see this recurring pattern, as I earlier said, and it always results to, it escalates an hazard because we believe it is a silent risk. Small leaks are ignored because they seem minor, but a leak creates a vapor cloud, and this find a source of ignition. So we see that these incidents don't escalate suddenly. They grow quietly because of poor inspection and delayed action. So I want us to note today that early reporting save life, and not just reporting alone, also ensuring you follow to letter to close out all what you identify in the course of the inspection. Now, this is another case study. Texas City Refinery, which happened, the incident that happened in 2025. So in 2025, at Texas City, 15 people died because of a tower overfilled. And the reason why they died is as a result of level indicators that failed and alarm systems that was what? Ignored. And the system failed at the engineering control level because they discharged flammable liquid into an open drum instead of a flare system. This is a classic example of a low frequency and high consequence event. So now I want us to look at this event closely. You will see that there is an engineering failure because the system relied on a weak engineering control and suffered from deterred maintenance and poor safety culture. And as I earlier said, this had resulted to a lot of catastrophic events, and that is why the major disaster happened. Because of what? Because of a system design and communication. Now, I want us to ask ourselves this question. What will you have done differently as a process engineer on duty? What would you have done differently as a process engineer on duty? Please write your answers in the chat box. Now, you're a process engineer. You were overfilling this Itowa, and you were hearing about some alarm because there was multiple alarms that was sounding. But despite the multiple alarm that was sounding, a lot of them still ignored the alarm. They keep doing it as they do because of poor safety culture. So I believe most of us also do today when we are in our different offices and there's an emergency drill, fire emergency drill, and you start hearing the alarm system. Some of you will sit down in your office. You say, it is emergency drill. Guess what? The day the real fire emergency will happen, it will not tell you. You will think it is an emergency drill. And at the end of everything, because of that poor nonchalant attitude towards emergency drill, you might end up getting caught up inside that. So Mr. Joshua said he wouldn't have ignored the alarm. Yes, he wouldn't have ignored the alarm and also inform others for them to probably evacuate and see if they can stop any of the machines. So let's continue. Now I want us to do this. Hope the class is not getting boring already. I want us to do this. If it's getting boring, please just say yes. Please don't be shy. Don't be shy. Always speak up. Just say yes. Is it getting boring? Type yes. Hello? I think I'm the only one in class with. Okay, thank you, Mr. Kayode. Thank you so much. Thank you, Mr. Thank God. Yeah,
No,
Mr. David Alabi.
it's not getting
Thank you so
boring.
much.
But
Thank you so much.
hello, can you hear
Yeah, I'm
me?
with you. Yeah, I can hear you.
Yes. Yes. So but please, I think everyone we've been here for over 1 hour, 30 minutes. So please, you can just stand up and, stretch your legs a bit. So
Yeah,
while
thank you
this
so much.
session
Ergonomic
continues.
break.
Thank you. Yes, economic break. Thank you.
Should I continue or we should wait for them to stretch?
And let's give them 1 minute to take an agronomic break. Just 1 minute. By 5:40,
Okay.
we continue. Thank you.
Okay, thank you so much. So me too, I'll use it to take economic break. Thank you so much. Sorry, I think are we done with our ego break? So we can continue.
Yes, we are.
Okay, thank you so much. So I will say welcome back once again to every one of you. And thank you so much for making this class a very interesting section. And I'm really happy. To this very moment, I'm still seeing 90 participants on the call, which is really a very great motivation. So thank you, thank you, thank you, thank you, thank you to my leaders, my ogas, and everybody on the call who are here to also just share up their little boy in taking this training. Yeah, thank you so much. So back to the discourse. So as it is, we we'll be doing a little break this thing now. Now let's go to the chat box. Now for the case study of the Texas City refinery that we earlier mentioned. So the first question, which hazard identification technique could have caught the field level indicator? Which hazard identification technique could have caught the field level indicator? You know that in the story we said there was a field level indicator, and there was a multiple alarm system that got ignored. You understand? So which hazard identification techniques could have caught the field level indicator? I want answers in the chat box, please. Yeah, thank you so much, Mr. Emery Obaru. Engineering controls could have. Engineering control is not an hazard identification technique. Yes, what if analysis is one. We talked about hazard identification tools. That's what I'm trying to test here. Azov, yeah, Madam Oluwatoyin, thank you so much. Bow tie, yes. So we have a lot of hazard identification techniques that would have caught it, because in the course of you carrying out your using your hazard identification tools, you will have identified what could go wrong. You will have projected what could go wrong. Mr. Emmanuel, administrative control, engineering control, all those ones are hierarchy of control. Yes, job hazard analysis. But the thing is, job hazard analysis still looks it still look peripheral, although it will have helped because assuming they did this for that particular job, maybe let's assume they do daily inspection. I'm just using that for an instance. Maybe probably it might have caught it. So this is some of them. So one is Azob or Hira. So those that choose Azob, Hira, yeah, we are all correct. So for the second one, at which level of the hierarchy of control did the system fail? For question number 2. At which level of the hierarchy control did the system fail? At which level? Wow. Wow, I love that. Mr. Julius Olabisi, correct. User, correct. Mr. Thangood, correct. Mr. or Mrs. Ejiro, correct. Mr. Engineer David Alabi, correct. Yeah, everybody's correct. So it failed at the engineering control stage. And the reason is because they use an open blow down drum instead of a flare system. So we are all right. Now let's go to the case study 3. Everybody must know about this popular incident, Piper Alpha platform incident that happened in 1988, which is one of the most massive fire incidents and explosion in North Sea platform, which resulted in 167 deaths. So I won't be diving too much in it, but I just want us to know that uh, in the incident, which I believe most of us know about this incident, Piper Alpha, the root cause was primarily traced back to failure in permit to work system. And even the most complex offshore systems can fail due to a breakdown in communication and administrative control. So I want us to know that it is very important we take systems and communication very, very, very serious because communication really matters too in the course of this thing. So another one, this one is very, very common when we talk about in-process safety issues. That is maintenance valve failure. A lot of people experiences this. If you are in the process safety space, oil and gas space, you will have been seeing this maintenance valve failure. So, and in this case, in this scenario, an incorrect valve alignment occurred during routine maintenance, and this led to an unexpected pressure buildup and resulting into a catastrophic rupture. So the lesson learned generally, if you to look at the word, an incorrect valve alignment. So that is, for them to have had an incorrect valve alignment, it was as a result of human error. It was as a result of what? Human error. So human error is predictable, and therefore systems must be designed to be what? Error-proof whenever possible. Because human error is possible. That is why we have some interlock safeguard in some machines that we use, because they know that some of us, because of human error, we can mistakenly slide our hand into the rotating part of the machine. So in the course of the design, it was being put into consideration that there could be an human error. That's why we have some of our safeguards that we use in most of our machines today. So human error is predictable. So this will now take us to the next slide we'll be talking about. But I want us to note as an engineer that no explosion is needed for a disaster. No explosion is needed for a disaster. A disaster it's not until when there's explosion before a disaster occurs. It can be as little as human error. It can be as little as system mismanagement, which can end up resulting to the catastrophic event. So this takes us to the next topic we'll be talking about, which is human factors in engineering. Human factors in engineering. So when we're talking about human factors in engineering, so majorly human factors, some of us overlook it. And that is why we see that most workers, when they're under pressure, they end up having issues when they're under fatigue. And I believe some companies, they've put into consideration what we call the shift system, whereby they run shifts. You understand? Maybe you work for so hour, another set take over, running the shift system so that it can reduce fatigue and it can give time for people to rest, most especially if it is a company that they need to run round the clock or they need to keep producing round the clock to meet up with their production targets. So we as human, because we are not robots, even our cars, which is our machine too, they run through wear and tears. They even end up packing up after sometimes if the maintenance culture is very poor. So due to this, what mistakes can happen? That's what you'll be thinking in terms of human factors in engineering. And part of it is what? The fatigue. Hmm? The fatigue, pressure to perform. Complacency is another very major one. Complacency, when we talk about behavioral-based safety, people believe in it, I've been doing it now. You even see some people telling you, even before they gave birth to you, this is how we've been doing it, and nothing has happened. I know it over sabi. Let me use that word over sabi. They believe I know it. They believe it is how we've been doing it and nothing has happened. So this complacency at the end of everything is an hazard on its own. It's a very, 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 very big hazard on its own. And at the end of everything, poor communication. If there is a poor communication and there is a mistake in communication, it can result to issue. For instance, let's assume I'm telling Mr. A, ensure that you push this to so pressure. And Mr. Hay didn't hear that pressure that I asked him to push it to and go and push above that pressure. It can lead to a catastrophic event. So that is why you always ensure you have a two-way communication. When someone communicates to you, always reassure and ask if the person understands what you're trying to communicate and not just giving the person a one-way communication, believing that the person understands what you've instructed the person to do. So system must be designed to prevent mistakes, recognizing that human error is what? Is predictable. So we have to design for reality. Let's be candid with you. Most people believe human error cannot happen, but we have to design for reality because human gets tired, they feel pressured, they get complacent. Most failures are not purely technical, they are human. Your systems must be error-proof because people will always what? Make mistake. Now, class exercise. Class exercise. Let's go to the chat box. A fuel storage tank scenario. Class exercise. Scenario number 1. You are inspecting a standard fuel storage tank during a high temperature afternoon. You are inspecting a standard fuel storage tank during a high temperature afternoon. Identify 5 hidden hazards. Let's go to the chat box. Let's see people's response. So what are the hidden hazards you can see while inspecting a standard fuel storage gap? Okay, high temperature. Okay, explosion, heat hazard. Yeah, I'm seeing more answers. Fire explosion, overflow. Good. So let's see more. Static electricity. Wow, Mr. Thank God, a round of applause for you. A standing ovation for you. High temperature, pressure buildup. Engineer Usu Oluwasegun. Yes, you are. Exposure to fumes. Mr. Emmanuel Oshe. Yeah, heat exhaustion, dehydration, fatigue. Now, look at what Mr. Emmanuel is doing there. Mr. Emmanuel, when we're talking about process safety, I mentioned it earlier that there's difference between personal safety and process safety. So that heat exhaustion, dehydration, fatigue, all those are speaking more to personal safety. Fire explosion, overflow are speaking to process safety. So do you get that, Mr. Emmanuel? Fire explosion, overflow are speaking to process safety. Mr. Emmanuel, can you unmute and confirm if you understand what I mean? So economic hazard, yeah, explosive atmosphere, engineer Emmanuel Ikeshuku, a lot of wonderful responses. So please, let's always understand the difference between process hazards and personal hazards. Do you get? So let me help you out. So now this is it. 1, overpressure during filling or due to temperature changes. Number 2, leakage, loss of contaminants and containment from seals or valves, static electricity during fuel transfer, fire explosion, risks from nearby ignition sources, and predictable human error, which is what? Overfilling. So I say a round of applause to everybody who responded in the chat box, and thank you so much once again. So I want us to always challenge ourselves to look beyond the obvious, as I earlier said. So you as an engineer, you should always look beyond the what? The obvious. Stop looking at the personal safety alone. Be looking into the system, be looking into the process safety. Because good engineer sees hazards. Look at that, what I'm about to say. Good engineer sees hazards. Great engineer sees the hidden one. Good engineer sees hazard. Great engineer sees the hidden one. So as it is, all of you are right. Different answers: overpressure from heat, static electricity during transfer, seal leak, fire risks from nearby grass, maintenance, human error during level check, and so on and so forth. So a round of applause to everyone. So let's go for another exercise. Look at this exercise. Now, a team is performing welding, hot work, near a live hydrocarbon pipeline. Near a live hydrocarbon pipeline. Look at that word, live hydrocarbon pipeline. What can go wrong? Monitor that keyword, near a live hydrocarbon pipeline. What can go wrong? And what controls are needed? Let's see our answers in the dashboard, in the chat box, sorry. What can go wrong? What can go wrong? Good. I've been seeing wonderful answers. Isolate, explosion, control, isolate, leakages. Thank you so much, my chairman, Madam Engineer Nimat. Leakages, explosion, heat transfer, catastrophic. For those I'm not mentioning your name, please, I'm sorry. So I'm just trying to scroll as fast as I can, but everybody are dropping an amazing answers. So I really say a very big thank you to every one of you for making this class interactive. You did not dump me alone to just be talking like a radio. Thank you so much. Vapor gas, Lotto for isolation, control engineering control, fire can happen. Thank you so much. Everybody has a very wonderful and amazing answers. So now, a team is performing welding job, hot work, near a live hydrocarbon pipeline. So that is a pipeline that probably a gas is flowing through, a pipeline, probably petrol product, crude oil is flowing through. It can even be welding of a pipeline. Welding of a pipeline. So what can go wrong and what controls can be put in place? So let me unveil my answers. So potential consequences: ignitions of fumigative emissions leading to fire or explosion. So, and also it requires what? The critical controls measures, continuous gas detection to monitor leaks. So this continuous gas detection is to monitor if there is a leak of any inflammable gas from the live pipeline, strict permits to work, which isolation procedure, firewall should be in place, and immediate access to suppression equipment. So I want you to know that no matter what you are doing, no matter the job you are carrying out, always ensure you have multiple layers of control, which is always often required for high risk work. And when you are also thinking of the control measures to put in place, always let's ensure we exploit and reinforce the use of hierarchy of controls, starting from the elimination till we get to the last result. Now, this takes us to bow tie model. Are we ready? If you are ready for bow tie model, say yes. If you are ready for bow tie model, say yes. Now we are getting there. If you are ready for bow tie model, say yes. You are good. Yeah, good. I'm getting the yes. Let the yes keep coming, please. Yes, good. So thank you so much. So when we're talking about bow tie model, this is another model that we use. We've talked about ASOP, we talked about what if analysis, and now we are on bow tie model. So bow tie generally speaks to a virtual tools showing the relationship between threats, events, and consequences. And when we talk about threats, causes leading to the event, what are the things that can result to that event? Those are what we call threats. What are the things that can result to the events we projected? Now, for instance, threat can be, let me give a very good example, like one of the example we used earlier, when there was a small leak. That small leak there is a threat, but the top event is the that, what are they calling it? Maybe a leak. The leak can be as a result of a corrosive pipeline. You understand? Maybe the pipeline has rusted, the pipeline is already corrosive. So that's the threat, which resulted to the leak. You understand what I'm trying to say? And the leak, so when there's now leak, it's resulted to the consequence where we had that explosion when there was a source of what? Ignition. But there's something about these barrier models. It's just like domino effects. So that is, if one barrier fails, another barrier is there to also what? Safeguard another barrier. So I want us to think of the time model as something like on the left, we have a threat where we call the corrosion. In the center is where the event is, which we mentioned that it is a leak. And on the right, which is the consequences. So as engineers, one of our job when we are dealing with bow tie model is for us to also ensure we build prevention barriers. And the prevention barriers will be now, okay, let me give an instance. Now, can you give an imaginary view? Like, look at threats. Sorry. Are you still seeing my screen, please? Good. Hello?
Yes, I can see
Hello.
see your screen.
Good.
Yes, we can see your
Now,
screen.
can you see the bow tie model that I'm projecting now?
Yes.
Now, see where my cursor is. This is the threat. Now, look at this threat. Let's assume the threat is the corrosion that I mentioned earlier, that the pipeline is corrosive. Now, the top event is the one at the center here, which I'm rolling my cursor, and the consequences is here. So, between this threat and the top event, you will always put a preventive barrier. So the barrier you're putting in place is to make sure that this threat doesn't end up turning to this top event. And in the case where this top event end up happening, you would also put a barrier here to stop that top event so that the consequences will not end up happening. Now, a very good example, the threat now is a corrosive pipeline. You understand? That is, there's corrosion. Now, you put some preventive measures to prevent the corrosive pipeline from leading to a top event, which is leaking. Do you get what I'm trying to say? And that leaking is one that will end up leading to that vapor clouding and so. So since you know that there is tendency that when this thing is corrosive, it can result to leaking of the hydrocarbon or the gas, then you now put another mitigative barrier here. So this barrier that you're putting there is that, okay, let's even now assume that there is leaking. How can we quickly arrest that leaking so that it won't end up turning to catastrophic events, which is the consequence? Fire, consequence, explosion. Are we together? Do you get my explanation? So as engineer, your job is to build prevention barriers to the left to stop leak and mitigation barrier to the right to keep that leak from becoming what? Explosion. This is how engineers should be thinking, not just identifying hazard and what leads to it and what happens after. That is, as an engineer, you should be thinking what leads to it. So what will lead to leakage? Corrosive pipe, right? What will happen after corrosive pipe? Explosion. So how will I prevent that corrosive pipe from leaking and from leading to leakage? That is your preventive barrier. How will I prevent that leakage, which now end up leading to vapor clouding, from leading to explosion, from leading to fire? That is where the mitigative barrier comes in place. So take threat as the hazard that you've identified. Threat is the hazard that you've what? Identified. The preventive barrier as the proactive control measures you've put in place to prevent that hazard you've identified to leading to the projected incident. Am I making sense, please? If I'm making sense, please type yes. If I'm making sense, please type yes. Okay, good. Thank you so much. So what we are trying to do there is that, you are trying to make that threat, which is the hazard that you've identified. You will now use a proactive control measures, which is the preventive barrier, to ensure that that hazard that you've identified does not result to the projected incident that you've been looking for. So event is projected incident. Mitigative barrier is a reactive control measure. So the reactive control measure, why do I call it reactive control measure? The top event has happened already. You have a corrosive pipeline. You don't want it to lead to leak. Then you put some control measures in place. After putting that control measures in place, at the end of everything, unfortunately, it still leads to leak. When it leads to leak, which you are trying to prevent, the next thing for you to do is to try as much as possible to put a reactive control measures to quickly mitigate that leak from leading towards the consequences, which is the outcome of the projected incident. So let's write. Threat is equals to identify hazard. Threat is equals to identify hazard or hazard identified. Preventive barrier, proactive control measures. Preventive barrier, proactive control measure. Event, projected incident. Projected incident. Mitigative barrier, reactive control measure. Remember, preventive, proactive, mitigative, reactive control measure. And consequences, outcome of the projected incident. Outcome of the projected incident. Now, just a quickly quiz just to ease up the classroom stress. Let's go into the chat box. So, who is proactive, who is reactive among these two professionals? Who is proactive, who is reactive among these two professionals? HSC engineer and doctors. HSC engineer and doctor, who is reactive and who is proactive? HSC engineers and doctors. Just to ease the stress of the class we've been going through since. Doctor is reactive, thank you. Exactly. So HSC are proactive. So we are trying to prevent our workforce from getting involved in any form of incident, in any form of an accident, sorry. And the doctor are the one that are now what? That are now doing the aftermath after the accident has happened. Yeah, thank you so much. Thank you so much. So I want us to know that, okay, let's do a live case scenario with this both analysis that we've learned now. Now look at this both analysis. So for a gas leak, do you get? Now the threat for a gas leak is external corrosion on a buried pipeline. The threat is external corrosion on a buried pipeline. So now, since you've identified the threat, which is the external corrosion on a buried pipeline, so what will you now be thinking of? What are the preventive barriers to prevent this external corrosion of a buried pipeline to lead to actual gas release, actual gas leakage? Are you getting? So the preventive barrier now is a robust inspection program and chemical inhibitor injection. Robust inspection. So the robust inspection program is to know if that pipeline is still very good, if the pipeline needs to be changed, if the pipeline just needs to be wedded. You understand what I'm trying to say? So a robust inspection program is for you to be able to identify the necessary control measures to solve the corrosiveness of that buried pipeline or injection of chemical inhibitors. And so now, what is the event that we're projecting? That is loss of containment. That is, by the time the thing is corrosive, over time, it might not be able to contain the gas anymore. And at the end of everything, there might be a vapor, a gas leakage, which end up leading to the ignition, like the example I gave earlier. So then, mitigative barrier. So what is the mitigative barrier that we can use when there is now gas leakage? Automated emergency shutdown. That is, if there's a gas leakage, if there's an automated emergency shutdown valves, immediately it detects that there's a gas, this thing, it will also automatically shuts down the process. Do you get the flow of the gas? And we have the gas system so in place. So by the time that is being put in place, it will prevent the leak leading to the consequences, which the consequences are always what? Fire, explosion. Fire what? Explosion. Thank you. So now the final quiz. The final quiz. Sorry that the quiz is getting too much, but that is the assignment Engineer Luaton gave to me. She categorically said she doesn't want it to be a theory. She wants it to be something relatable and practical. Even though I'm not sure if I'm meeting up with the assignments, but after my presentation, I think she will decide if I try or not. So the final exam quiz. So this is the question. Now go to the chat box. What is the core focus of process safety? 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 Waiting for answers. What is the core focus of process safety? Yeah, good. To prevent catastrophic events. Yeah, good. I've gotten my answers already. To prevent major events. To prevent the release of hazardous chemical. Yeah, it's still catastrophic events. Yeah, preventive approach, proactive prevention of a hazard. Yes, wonderful. To prevent deadly event leading to explosion in the event, to limit catastrophic events, explosion. Sorry, Engineer Abel, don't write to limit catastrophic, to prevent it. Don't limit it at all. Prevent it, eliminate it, remove it. To prevent major accidents. Yeah, to prevent loss of, yeah, good, 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 good. So let me see if everybody is correct. Well, let's check if our answer is correct. Let's check if our answer is correct. So the answer for everybody that said preventing catastrophic release of hazardous material energy. A round of applause for you. So now the next question is, in a bow tie diagram, what is the purpose of prevention barrier? In a bow tie diagram, what is the purpose of prevention barrier? In a bow tie diagram, what is the purpose of prevention barrier? Don't forget that bow tie, I said threat comes first. Yeah, proactive to stop threat from leading, to stop threat from leading to top events. To stop threats from leading to top events. Yes, to arrest threats. Yeah, proactive control measures. Yes, to prevent top events, to stop threats from to stop top events from happening. Engineer Ejiro, to stop top events from happening. It is a proactive control to stop threats from leading to top events. Yeah, good. So let's check if we are correct. So now look at our answer. To stop the top event or leak from happening in the very first place. That is trying to prevent threats from getting matured to top events. So another question for us. True or false? If the likelihood of a disaster is very low, engineers should focus their budget elsewhere. If the likelihood of a disaster is very low, engineers should focus their budget elsewhere. True or false? True or false? Again, let me start saying false, false, false. Haba, nobody's supporting me. True. False, false, false. If I tell you everybody who chooses false is wrong, Uncle, will you believe me? But anyway, the correct answer is what? Is false. A round of applause for everybody. False. So, again, let's check the right answer. So, yeah, false. High consequence events are always critical risks. So that was why I explained using the car and aeroplane as an example earlier in the program. So now the last question. As a young engineer, what is your primary responsibility if you see an unsafe condition? As a young engineer, what is your primary responsibility if you see an unsafe condition? As a young engineer, what is your primary responsibility if you see an unsafe condition? As a young engineer, what is your primary responsibility If you see an unsafe condition, report it. Yeah, good. Immediately take action. I love that. Stop it, escalate, stop it, stop the work and fix it. Good. So, thank you so much. Report and follow up. I love that statement. Report and follow up. Enforce stop work and report. Highly impact lecture. Please, can we have the recording? Madam Oluwatoyin will respond to that. Stop the work and report immediately. Yeah, thank you. Thank you. So the answer, gang. Report it immediately. All personnel have the right and responsibilities to raise concerns. So now, let me emphasize more on the roles and responsibility of the young engineers. And this is our roles as a young engineer. You have the right and the responsibility to speak up when something doesn't look right. You have the right and responsibility to report near misses without fear, and they are learning opportunities. Let me make you understand. Near miss, the higher or the more the near miss that is being reported, the more the safety culture is being positive. Because when people can speak and report more near misses, then there's high chances that you get to learn and quickly put in necessary control measures in place. And as a young engineer, always ensure you apply process safety thinking in every design decision you make. Now, let's start thinking about process safety and let's elevate from only personal safety. We should start thinking about the process. What can go wrong? So now I'm challenging you all to identify one process hazard in your workplace this week and share it with your supervisor. I repeat, I am challenging you all as a way to appreciate this lecture, to identify one process hazard in your work area this week and share it with a supervisor. So on a final note, hazards are everywhere. Small issues can escalate into disasters. So I want us to know that small issues matters as they can result to big disaster. I want us to start thinking about systems. And for heaven's sake, always pick up early. Always pick up what? Early. If something doesn't look right, it probably isn't. If something doesn't look right, it probably what? Isn't. Most incidents don't happen because we don't know safety. They happen because we stop thinking about hazard. I repeat, most incidents don't happen because we don't know safety. They happen because we stop thinking about hazards. So, on a final note, I'm going to leave you all with this. You are not just an engineer. You are risk managers. You are not just what? An engineers. You are risk managers. Note, your decision saves life. And as for engineers, it is expected of you to anticipate failure because every calculation you make and every permit you sign determines one thing. Should I tell you that one thing? Do you want to know that one thing that it determines? If you want to know, you just type yes. Type yes in the chat box. Yes. So I want you to know that every calculation you make and every permit you sign determines one thing. And that one thing it determines is whether your colleague go home safely at the end of the shift. Whether your colleagues go home safely at the end of the shift. Always remember that a safe engineer is a productive and efficient engineer. A safe engineer is a productive and efficient engineer. Thank you so much and enjoy the rest of your evening.
Please, I expect to keep seeing the round of applause. Like it should be coming and it should be giving it some very beautiful reactions. And also, please do encourage and do appreciate our facilitator through the chat box as well. Thank you, 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 Mr. Hakim. You have done beautifully well and you have delivered excellently well. Thank you so much for this wonderful training. We can't record this. We can't say this is a webinar. No, this is full blown out training that you have done and you executed it perfectly. Thank you so much, sir. We are sincerely grateful. Thank you, thank you, thank you, thank you, thank you. We are not clapping. I thought I'll still be saying the clapping emoji. Yeah, thank you so much, sir. So, I know it is very important to take questions, but our time is fast spent. I'll just be giving opportunity for two questions, please. Two questions, please. So if you have a question, it's please just one question each. Not a question that has babies, okay? Please, two questions each. Two questions, right? So please, if you have question, can you just signify by raising your hand or by typing it out in the chat box? If you have a question, signify by raising up your hand or by typing it out in the chat box. I'll just give us 1 minute to do that. Otherwise, we'll just proceed to the next item on the agenda. Please also, the attendance has been dropped in the chat box. Kindly document your attendance if you want to have access to the recordings and also to the lecture materials. Thank you. All right. So I would call on Mr. Minakoro Joshua. Please, your hands are up. You have the floor for your questions. Thank you. Hello, Mr. Joshua. Are you still with us? Our lecturer is a he, Mr. Hakim. Mr. Joshua, are you still with us? We can't hear you. All right. Just moving forward. Let me just share my screen again. Okay. Please do confirm you can see my screen. All right. So, thank you very much. In the absence of questions, we would be moving straight up to the presentation of certificates. On a very short notice, Mr. Akim came through for us and he delivered excellently well on this training. And it is we can I mean if we had the whole world, we would give it to Mr. Hakim this at this point. But we would just want to present to him a token of appreciation from the Young Engineers Forum of Nigeria NSC Kejo branch. We would like to present to Mr. Hakim a token of our appreciation for this wonderful session that he has taken us through. So I would call on the chairman of the Nigeria Society of Engineers, NSC Kejo branch, Engineer Nimot Muili, FNSC, to please handle the presentation of certificates. Thank you very much, ma.
Thank you very much. Please, can we applaud our presenter again, once again? I mean, I got stuck. I've been in transit to the secretariat. At the point when the network locked me out, I had to call on the phone coordinator to get me back in the class. We really, really appreciate. Please, let's really applaud them. This is a master class. We really had a very good time. Thank you very much. And I trust that we'll be able to call on you subsequently for another session. Thank you. On behalf of our past chairman, to lay the foundation for us to have this platform. And on behalf of the past YEFoN coordinators as well, they lay the foundation. Then on behalf of myself and the young engineer coordinators, I want to proudly present this certificate of appreciation to Mr. Akim Mukhtar for sharing that insightful session with us on the process safety and hazard analysis. The training is not only for those in the oil and gas. I know it's heavy in the oil and gas, but this is really very insightful. For those of us that go on construction site, in the manufacturing sector, across board, even in your home, we see sometimes explosion happen, sometimes because of heat, sometimes because, small things. So thank you for opening our eyes to this very insightful session. And I trust that we all take it very seriously and also grow ourselves in it. Thank you very much, Mr. Akim Mukhtar.
Well, thank you so much, Ma. I am very, very happy and I really appreciate this certificate. And it's really a privilege to be here and to take this training. It's really an honor. So thank you so much, Ma. And I hope I
You're
was able
welcome.
to meet up with the scorecard of my engineer Oluwatoyin, who wanted to be a practical destined before I accept it. So hope I met up before I accept the certificate.
You over exceeded the target that was set for you, sir. Thank you so very much,
Yeah,
Thank you so
sir.
much.
thank you.
Thank you
Thank
so
you.
much, sir.
Thank you so much.
Thank
So,
you, sir.
Engineer Nimat, thank you so much, Ma. I'm very grateful for the
You-
certification. And
You're
thank you to
welcome.
all the Young Engineers Forum of Nigeria and the Nigeria Society of Engineers at large. Thank you so much. I appreciate this.
A pleasure. Thanks a lot. Keep inspiring.
Thank you all very much. Please, the attendance has been dropped. The link to the attendance has been dropped in the chat. Please document your attendance. We will share the recordings and also share the slides with us. And as well, do follow Mr. Hakim on LinkedIn for everyday safety tips. Every day he posts safety tips on LinkedIn. So please follow him on LinkedIn as well. His LinkedIn handle is Hakim Ayodele Mukhtar. So please follow him on LinkedIn as well. Connect with him on LinkedIn. And you can also reach out to him after the class as well. Thank you very much. Our time has been fast spent, so we'll just move straight up to the closing remark. I would like to call on my predecessor, the immediate past coordinator of the Young Engineers Forum of Nigeria, NSE Ikeja branch, who is currently the ex-official of the Nigerian Society of Engineers Ikeja branch, Engineer Yusuf Abdulrazak MNSE, to please take us through the closing remarks. Thank you very much, sir. Okay, I think he has dropped off from the call. Um, all right. Well, since he's no longer on the call, please permit me. Okay, the other person I wanted to call, Tito, he has dropped off. Okay. Engineer Yusuf, yeah, you are back on the call, please, sir. The closing remarks.
Hello, please confirm if you can hear me clearly.
Loud and clear, sir.
Hello.
Yes, we can. Yes, we can. We can hear you. Engineer Yusuf, we were hearing you, but now you are muted.
Okay, thank you very much. On behalf of the Young Engineers Forum, it is my pleasure to actually do these closing remarks. So as we come to the close of this enlightening webinar, I want to sincerely thank everyone for your active participation and presence. We have had the privilege of learning from our most experienced scholars from the oil and gas industry who has shared from his wealth of experience with us. Today's session has really been rich and insightful.
Think he has dropped off network or so. Um, Once again, I would just like to say thank you to everyone for joining us in this wonderful session. Thank you to our highly esteemed facilitator. I also want to say thank you to the branch chairman, Engineer Nimot Muili, for giving us this great opportunity. We had on the call Mr. Waliu. We also had on the call the General Secretary of the Nigerian Institution of Safety Engineers, Mr. Kende was also on the call as well. We also had people from the sustainability people that were on this call as well. And we want to say thank you all very much for joining. So all the young engineers and to other professionals that were on this call, thank you so very much for joining. We would move now to the closing prayer, which I would like us to please all unmute and take. But before that, I would like us to please take a virtual, for those who are still online, please let's just take a virtual picture, please. Just quickly, just take a virtual one. Yes, so that we can all, have this on record, okay? Please, for those who are online, let me stop sharing my screen so that I can have the full grid view to myself. Yeah. Okay. Please, can you, you know, start your video? Okay. Please, Mr. Sani, Madam Fomi, can we start our videos so that we can, just take this? Yeah. Steph Mandy, Mr. John, Madam Peace, please let's just get our videos on so we can quickly just take these snapshots before we leave and take the closing prayer. Our facilitator, Mr. Hakim, we cite you. All right. So quickly, let's just do this as quick as possible. All right. For those who are on, I'm just gonna take it now. Okay. One. Just a moment. Okay. And put second screen. Okay. All right. Thank you all so very much. Thank you, thank you, thank you. You can close your videos now. Thank you, thank you, thank you. We would be taking the third stanza of the national anthem. You can please unmute and take it together. Let's just unmute and take this together. O God of all creations, grant this our one request. Help us to build a nation where no man is oppressed, and so with peace and plenty, Nigeria may be blessed. Thank you all. We would also be taking the branch anthem. Okay.
branch of the NSC, like Ikeja branch. He's the 32nd branch of the NSC. He's a branch to march. Building a viable. Branch of the NSC, like Ikeja branch. He's the 32nd branch of the NSC. He's a branch to march. Building a viable engineering culture, dedicated to bring out the best and to nurture the best of the best. The second to none is Ikeja branch. The best of the best. The second to none is Ikeja branch. With God on our side, will be no fair and wide, where the branch to watch. With wisdom we will lead, and discretion we will build, will be known for certain. Together we will make a great nation, proud, innovations and professionalism all around. The best of the best, the second to none is Ikeja branch. Second to none is Ikeja branch.
Thank you all so very much. Thank you for your time. Thank you for your attention. We had spent approximately 2 hours 30 over 2 hours 30 minutes on this call. So thank you, thank you, thank you. Thank you, our facilitator. Thank you, our chairman. Thank you to everyone who joined in on this training session. Please, you can network with the people on the call for the next 2-3 minutes. And after that, thank you, Ma.
I really enjoyed this. Thank you. It was quite insightful.
Thank you, Ma. Thank you.
Yeah.
Yes, Ma.